Hello, everyone, and thank you for joining the first podcast of AstrumDrive Technologies. Let me start with introducing myself. My name is Ivailu Vasilev, and I'm the CEO of AstrumDrive Technologies. Here we're developing advanced propulsion systems, and now we spend significant amount of time and effort to develop the warp drive technology. We do that because we see the future of the humanity among the stars, and we feel that this will be a bright and exciting time in which also the future of our kids is going to be secured. Because as Carl Sagan said, the civilization either becomes spacefaring or extinct, which actually happened many times in the history of the Earth. For example, all of the dinosaurs were wiped out from the face of the Earth in a single day by a asteroid which hit dirt in the Earth in the Gulf of Mexico. So we want to make sure that this never happening again. And today we're also joined by Nelson. He's the head of our physics department. Nelson, please go ahead and introduce yourself.
Hello, everyone. Thank you, Bailo. My name is Nelson Bolivar. I'm head of the physics department in AstrumDrive Technologies. Also, professor of physics at the Central University in Venezuela. I've been professor there for almost 15 years so far. And currently, I'm also holding a postdoctoral fellow at the Balseiro Institute here in Argentina, doing some research in physics.
Thank you, Nelson. And Nelson is too humble, actually. He was the head of the physics department in the University of Venezuela before he joined AstrumDrive for a full time. And Nelson, let's start maybe with a little bit of explanation, which is going to give better understanding of to our listeners about the warp drive. So, can you please explain the warp drive in several sentences, in understandable way?
Sure. Essentially, a warp drive is a mechanism that uses uh, uh, possible solutions. I mean, of Einstein's equations, so you propose some specific space-times that can manipulate, in a sense, and somehow you can say slide or deform space-time, so you can move in apparently faster than light without breaking any physical law. Which, by that I mean, you cannot move faster than light if you are certain type of observer. But in this scenario, in this configuration, you don't violate any of this. I mean, special relativity tells you the top velocity in the nature is the speed of light. And with this configuration, you are an observer that is not violating that, but you are moving through space-time in a way that these deformations allows you to move with respect to an external observer in a almost any speed you like without violating yourself. In a sense, you are in a bubble, and there is an inside of the bubble where everything goes okay for you. You don't violate physical laws, and there is an external space-time outside the bubble where observers don't know exactly what's going on inside, but they see as you move very fast.
Right, so actually, the warp drive reminds me a lot about Star Trek. So you remember that the spaceship is in one star system, and after that it goes to the uh, hyperspace and goes to another star system. So I guess it's pretty much the same. And I just want to point out something I hear you saying. So to the best of my understanding, the warp drive doesn't violate any physical laws. It is working according to the general relativity equations of Albert Einstein. Is this correct understanding, Nelson?
Yes, in a sense it is, but in another sense it's not. And in fact, it all begins with Alcubierre in the early 90s, by the way, inspired in Star Trek. uh, and his solutions, uh, they are analytically correct. They also agree with Einstein's equations. Uh, but this is like a very simple solution. You have Alcubierre in the 90s. He made his contribution by thinking in this type of bubble, but then you need some matter to do that. And that matter you need, as a matter of fact, it became with a terrible drawback, which is that you need a negative density energy to accomplish to sustain this bubble configuration, which is something that is not physical. Not only that, you have other drawbacks. For example, you need a lot of this matter. And the first calculations, it looks like all the matter in the universe wasn't enough. Now, in the early 2000s, Natarios came with a second set of solutions. These two are the most known and probably the only two known. And this one reduces a lot these problems, but still we have the negative energy problem, which is a very important thing, which, by the way, is one of the first things that we are approaching in our research here.
Also, to the best of my understanding, we say that the warp drive is physically possible. It doesn't violate any equations. So according to the general relativity, we can move faster than light. But on the other hand, right now we don't have a clear idea how to make it in a way in which is uh, physical, meaning that we can reproduce it in lab. And is this correct understanding?
Yes, there are no physical laws that prevent that. In fact, it goes go according to physical laws like Einstein's equations, as far as we know, right? Of course, there are these limitations exist, but also one of the most important thing is that we don't understand completely. We have a really large understanding of general relativity, but when you push to the limits, which is in this type of situations, we don't understand exactly what space-time, how space-time behaves, which are the physical law, how much can you push the model in this case. So it is well understood that if you have a solution of Einstein's equations, this makes physical sense as far as you can physically observe this situation. So we don't have anything that you can use in the lab because, in fact, it's the negative energy is one of the largest problems. But for the other hand, we have a very simplified model that we use in the theoretical approach. So we need to complicate that approach too and see what is really telling us the model, uh, and then look forward for which is the model that is going to represent the best option for our warp drives.
And Wilson, to the best of my understanding, right now there are a lot of groups which are doing research in the warp drive. For a fact, I know that there is a special lab Eagle works, I believe, in NASA, and also I know that DARPA is doing a lot of research in the field. And recently there were some articles that everybody got excited about them, that a first warp bubble has been created in the lab. And also I know that there are strong teams in the Latin America which are working on the warp drive. And do you mind explaining in a little bit more details what is the difference in our approach in comparison with all other groups which are currently working on the problem?
Sure. Yeah. As you said, there are several groups already working on this. There are very good people working on the field, really, really good people. Especially here in Latin America, there are strong groups in Brazil, for example, working on this. And there has been a lot of recent attention to this research. Last year was an exciting year. There's some articles, a couple of articles lead us in some very interesting directions, trying to avoid some of the problems and solve others. Well, it's been attracting a lot of attention. For us, our approach is going to be like the next step for up to this research from last year. We are usually research goes in the direction of looking at what's going on with what we call the left hand side of the Einstein's equations, which is what it involves geometry. Uh, and we are going to focus more on the right hand side, which is what it concerns to matter. And this hasn't been explored too deeply, and our approach is going to be to really go a step forward and complicate the situation instead of using, for example, a perfect fluid with some specific equations of states. We're going to complicate it more. We want to add anisotropies. We want to add thermal dissipation. We want to add electromagnetic fields. We want to see what this interaction between all these forms of energy can bring to us. Then we will bring also complicate this using some equations of states. For example, some polytropic equations of states have been used, but we want to use it in the context of anisotropies and see what is the matter can tell us about these conditions of energy that are being violated, and how this matters configuration can also have and will have an impact on the geometry of space-times that we need to have. So in a sense, if you change matter, we will see some need of changing probably geometry, and that is like playing a balance probably, and that's going to be our approach. So we'll start with matter, and then looking for physical configurations, possible configurations, we'll start modifying the model and perhaps obtain our own versions of some metrics.
And also, my understanding for the majority of the research groups which are currently working on the problem is that they're closed, so they don't share much of their internal works. But here we want to do something different. We want to share the research with pretty much everybody on internet. So if somebody thinks that it's interesting or you have ideas, guys, please interact with us, because it's very difficult problem to crack, so we need a lot of help. Nelson, do you want to add anything about that?
Oh yes, this is really yeah, it's a really complicated problem. It requires several fields in physics. I mean, it requires a deep understanding of general relativity. It requires also quantum field theory. When you talk about matter and dynamical matter, you need quantum field theory, which is really complicated by itself. It requires a lot of knowledge, a lot of ideas. You have to think out of the box as much as possible, and still following the physical laws, still following, not disrupting too much in the know knowledge that is in the field. And so, with that in mind, all the help we can. I mean, everybody is welcome, I think, to to give us some ideas, to give us some of his insight. And yeah, we need as much help as we can get to solve this problem, uh, which is going to be really, really exciting, I think.
Yeah, I agree, Nelson. This is one of the most exciting things I ever worked on. So if somebody listening this podcast is feeling in the same way, please get in touch with us. And Nelson, you spoke a little bit about what is the different in our approach to the problem. And we started working on the warp drive research among with other projects we do in AstrumDrive Technologies about a year ago. And I remember we went through many concepts until we were able to find the right direction. So I know that we dealt a lot with the Rindler horizons, with bubbles in space-time. Do you mind to give our listeners a little bit of background? What did we do in the last year, and what are the next steps for us in solving this problem?
Yes, of course. Yes, well, as you said, we started, I mean, besides all the projects that we are already working on, we started by looking at the problem in a different way. We thought about the bubbles, the space times, and we follow several roads. For one side, we follow for a while how to understand space time with a different model. For example, we look a bit about how fluid models can be used to represent the space time. But also then we went to the bubble itself, looking at what a bubble of space-time itself is doing. In that sense, we did some research about different type of horizons that can appear, rendered horizons, for example. It depends on the observers that you have. Also, we thought about how this will implicate some radiation, decaying of these bubbles. Uh, and that led us slowly, but the research led us to the exactly to see what is how it's going to be the evolution of the bubble once it's already formed. And then this scenario is where Cuvier's and Natarios solutions appear, which is at the original works. Uh, so in that sense, then we find out that the complication is to understand, for one side, what it could be negative energy in different scenarios, and on the other hand, you want to understand how this bubble is going to move, how it's going to move at all. So yes, so in that direction, then we took these solutions. We're studying these solutions. We already studied Alcubierre solution, and then we are currently understand it better. Natarius solution, which is a more general in a sense than Alcubierre's. Alcubierre's is a particular solution of Natarius. And with that in mind, then what we are doing to this point is well, learning exactly how to construct the whole configuration, which means that you have a bubble and then you have something inside the bubble. This something is probably an observer in some spacecraft, and you have a space-time inside, and then you have a space-time outside, and you need to see how correctly match those space-time together. Unique junction conditions that are currently have to be written correctly, and this is there are easy scenarios where you do that. For example, you have flat space-time outside and something like that. We want to, yeah, also again complicate this situation more, and so we want to understand correctly different approaches to the junction conditions, which are a couple that we already know, and then construct the junction conditions. Then we have all the equations, Einstein's equations for the configurations you have, space-time inside and space-time outside. And from that point, then add matter and see what's going on with this matter. And the matter could be in different forms. I mean, you have a matter that could be distributed inside somehow. You have matter that can be distributed at the edge of the bubble, and this is it won't be evenly distributed. You will have anisotropy. You will have a lot of enrichedness in the approach. And from that point, using equations of states, of course, that we need to solve Einstein's equation, we expect
Correct.
to solve and obtain the first pair results for interesting publications.
Yep. Nelson, thank you. This was a great overview. Uh, from my side, I just want to add one more thing that we're planning to share with you guys some of our daily stand-ups. So we're using Gearboard, so we're going to share the screen so you can see the current tickets we're currently working on. And Nelson, before we close for today, do you have anything else to say or share?
Uh, yeah, well, I want to invite again everybody to join us to support us.
On this
We need
journey?
Yeah, this is going to be an exciting journey. We need all the support we can get. I mean, intellectual support, financial support. This is something really, really great, and it's growing. It's a field that is growing, and you cannot imagine how how much excitement you feel when you start to find out that these things are maybe are possible, and maybe not for us but for our kids. The stars are in the horizon and maybe we can reach them some at some point. And who's going to start this journey? Well, us
Thank you,
together.
Nelson. I cannot, honestly, I cannot put it in a better way. Well, everyone, thank you very much for listening. Our first podcast. As I said, we're going to start sharing some of our daily stand-ups with the rest of the team. And so if you like what we do, please support us. Like the video, share the video. We're going to share the Patreon link under the video description, so please check it out. And thank you very much, and let me wish to all of you to have a very nice and successful day. Thank you.